Look at a fighter jet at an air show, and you'll see a machine built to treat gravity like a suggestion. They pull enormous G-forces, flying completely inverted with zero hesitation. Then we have modern commercial airliners. A Boeing 777 can carry hundreds of passengers and enough fuel to cross an ocean. So what exactly prevents this highly advanced machine from rolling over and doing the same thing? Many assume a passenger jet is simply too heavy or physically incapable of rolling upside down, but history proves otherwise. In 1955, Boeing test pilot Tex Johnston climbed into the cockpit of the Dash 80, the aircraft that would soon become the legendary Boeing 707. During a demonstration flight, Johnston executed a flawless, complete barrel roll in this massive four-engine prototype. The airframe handled the inversion without damage, but Johnston's stunt relied on keeping positive G-forces pushing down on the plane throughout the maneuver. Tasting through an upside-down position is one thing. Simply hanging there is a completely different story. And if the plane doesn't break when it flips, we have to look elsewhere to see what actually stops it from staying inverted. The first thing most people blame is the wings. Passenger jets have highly specialized wings, heavily curved on the top and flatter on the bottom. It seems logical that if you flip that shape upside down, the lift vanishes and the plane drops. In upright flight, lift depends on the airflow direction and the wing's angle of attack. If we rotate the wing 180 degrees, it can still generate upward lift. The pilot just adjusts the angle. It operates less efficiently, but the wing itself keeps working. Because the wings still function when flipped, the true limitation must be hiding deep inside the aircraft's internal systems. Commercial jets are engineered with one massive, invisible assumption built into every single system. Gravity will always pull downward. And that vulnerability starts right inside the wings. Inside a passenger wing's internal fuel tank, gravity pulls thousands of liters of liquid fuel at the very bottom, precisely where pumps wait to draw it in. But when the aircraft rolls over, the fuel instantly falls toward the ceiling, leaving the pumps completely exposed. Instead of drawing in liquid fuel, they start sucking in empty air. Jet engines require a continuous flow of liquid fuel, and they rapidly shut down when fed air instead. The engines would also begin destroying themselves from the inside. Highly pressurized metal bearings and fast-moving shafts rely on oil systems that also use gravity to collect and circulate lubrication. Without that downward pull, the oil scatters. Within moments of sustained inverted flight, the aircraft's mechanical organs would starve of fuel and oil, tearing themselves apart because the gravity they rely on is pulling the wrong way. Even if engineers could somehow fix the engines, the environment inside the cabin would become a nightmare. When an aircraft stays upside down, everyone inside experiences negative G-forces. Instead of feeling heavy and pressed down into your seat, you are violently pulled upward, away from the floor. The chaos would be immediate. Anyone without a seatbelt would fall straight to the ceiling. Laptops and heavy bags and large food carts would instantly become airborne, acting as dangerous projectiles. And human biology protests just as aggressively. This is what pilots call a redout. Negative G-forces force your blood to rapidly rush upward, pooling in your head and eyes. It causes immediate pain and loss of vision. Humans simply tolerate being pushed down much better than being pulled up. Between the flying debris and the biological strain, the passenger cabin is incompatible with sustained inverted flight. Aerobatic and military aircraft bypass these problems. They use specialized flop tubes that physically move to follow the fuel, alongside pressurized oil systems designed to ignore the direction of gravity. If the engineering solutions clearly exist, why do commercial aerospace engineers actively choose to leave them out of passenger jets? It comes down to purpose. A commercial airliner isn't built for combat or airshow stunts. Its singular mission is to transport hundreds of people safely, efficiently, and comfortably from one airport to another. Adding inverted fuel pumps and complex pressurized oil systems would introduce massive amounts of extra weight. In aviation, extra weight means high fuel costs and reduced passenger capacity, all to solve a problem that commercial airlines never encounter. A commercial jet is a perfectly optimized machine. It can carry incredible loads across entire oceans with extreme reliability, because every piece of its design leverages one unyielding assumption, that gravity will always be exactly where it belongs, beneath it.